In this example, we're going to sketch the graph of y equals x minus cos 2x. As part of this function is a trigonometric function, we're going to be measuring using radians. The other thing you need to notice is that my domain has been restricted, and I'm only allowed to use my domain from minus pi all the way up to pi. So if I show you the graph, you can see more or less what the graph is going to look like. But we're only going to be looking at the graph within the boundaries of the two red vertical lines. If I take a look at this, it looks like I'm going to be finding 1, 2, 3, 4 stationary points, and I'm going to see whether those are local maximum or local minimum stationary points. I'm also going to make sure that I know exactly where my y-intercept is. If I know that they are local maximum and local minimum, I immediately can understand the gradient of the curve, because it will be increasing towards a maximum and decreasing from it, or decreasing towards a local minimum and increasing to the right of it. We're going to start by finding our stationary points. In order to find my stationary points, I must make sure that I can find the derivative of the function when it is equal to 0. So finding the derivative of the function y in the variable x and making that equal to 0, I should be able to find where I'm going to have the x coordinate of my stationary points. The derivative of x is 1, and the derivative of cos 2x is the derivative of a composite function. So first of all, I have to take the derivative of cos 2x, and that's going to be minus sine 2x. So that must be minus minus, which is plus sine 2x. And then the derivative of the inner function 2x is 2. And I'm going to put that coefficient at the front of the term. And I'm going to make that equal to 0. If I want to solve to try and find x, I first need to get it so that I have function angle ratio equal to a numerical ratio. So I will then have sine of 2x is going to be equal to minus 1 all over 2. You can see that this is a normal trigonometric equation. And now I'm going to solve to try and find x. The first thing that I do to find x is to find where is my sine function going to have negative ratios. And if I draw the Cartesian plane, we know that I'm going to get negative ratios in the third and in the fourth quadrants. The next thing I need to do is I need to find a reference angle. And my reference angle is going to be when sine is a half. So the reference angle for this particular equation is going to be the following. We said that our solutions were going to be found in quadrant 3 and quadrant 4. So using the information in quadrant 3, I would find that my angle, which is 2x, was going to be equal to pi plus my reference angle. Remember, that is also plus k times the revolution, which is the full period for the sine curve, and that is 2 pi. And also remember that k is a natural number. In the fourth quadrant, my angle would have been minus the reference angle plus k 2 pi. Now all I need to do is I need to simplify these two answers in the third quadrant and the fourth quadrant. These are my general solutions. And once I have my general solutions, I'm then going to test them to find exactly which values I could have for x in my given domain, which was from minus pi up until pi. By adding our like terms and then dividing them by the coefficient of x, which was 2, I find that in the third quadrant, I would have got that x is going to be 7 pi all over 12 plus k times pi, and in the fourth quadrant, x was equal to minus pi all over 12 plus k times pi. Now to test to find out what the x coordinates could be in my domain, I'm going to make k 1, -1, and 0. The chances are that I'm not going to have to test any further for k. Do this on your own. As this is part of core maths, you should be able to do this quite easily. I'm going to now just tell you your solution set, and you are, as we predicted, going to find 4 values for x. Now, if you take a look at these values and they are written as common fractions in terms of pi, it's not always easy for you to understand exactly what that value is. So I'm going to write the solution set in decimal form, rounded to 2 decimal places. The 4 solutions that I get are when x is going to be -1, 3, -0, 26, 1, 83, and 2, 88. What I want to do next is I want to test whether these stationary points are going to be local minimum or local maximum turning points. Let's do that by first finding the second derivative of our function. As the second derivative is the derivative of 1 plus 2 sine 2x, I find that the second derivative of the function y in the variable x gives me an answer of the derivative of 1 is 0, and then the derivative of 2 sine 2x is going to be 2 times cos 2x, all times by the derivative of the inner function, which is 2. And if I simplify that, I get that the second derivative is going to be equal to 4 cos 2x. In the next part, I'm going to take each one of these x values that I got from my stationary points, and I'm going to put them into the place of x in my second derivative. Remember, if I put it in and I get a negative answer, then it's a local maximum. If I put it in and I get a positive answer, I have found a local minimum turning point. Hopefully, when you got your answers, you realized that you had a local maximum when x was -1, 3. By putting that x value back into my original function of y, I can find the y coordinate of -0, 44, and I know that the point now for that local maximum turning point is -1, 3, -0, 44. Doing this for the other 3 turning points, you can gather the shape of your curve. There's one more thing that you need to do, and that is to find your y-intercept. If you substitute 0 in the place for x, you find that your y-intercept is going to be at 0, -1. Now lastly, if you just wanted to find out exactly what would these points be over here at the boundaries of the domain that you would want to use, you would put -pi into your function of y, and you would find the corresponding y coordinate. And when x was -pi, your y coordinate was -4, 14. Likewise, doing it when x is pi and substituting pi back into your function of y, you found that your y coordinate was going to be 2, 14. You have now very successfully found the curve of the graph, which was y is equal to x minus cos 2x. Please remember, every time I include a trigonometric function, you must work in radians.